Hello, welcome to this course, EMEE6002, Sustainability and Climate Change. We are going to learn a series of new energy that helps to reduce carbon emissions. The first topic is nuclear power. So why do we need to develop nuclear power? Okay. In the first lecture, we talked about the climate change. One of the main causes is because of the greenhouse gases. So we are now trying to find new form of energy that does not emit carbon. So in the modern society, we still need energy. So we can't stop any energy productions, and we need to find another alternative energy source. So far, you can see most of our energies come from coal or some from the natural gas as well as oil. And regarding the percentage of using nuclear is only 13% something. Now the figures is improving, but still under 20. So let's start talking about the fundamental knowledge on nuclear energy. There are two forms of nuclear reactions. One is called nuclear fissions. Fission means we split a large matters into two smaller matters. And during this process, energy is released. So according to Einstein's equations on relativities, energy is equal to delta m c squared. Delta m is the change on mass in the nuclear reactions. During this process, some mass is lost and converted into energy. So if 1 kilogram of energy is lost, then C is the speed of light, 3 multiplied by 10 to the power 8. So this number will be in the order of 16 because of square, and this is a huge energy output. So in nuclear fissions, why is it so powerful? Now because of the equations, we know that it's related to C squared, which is a huge number. And also during this process, we are breaking the nuclear bonding within an atom. So by breaking this nuclear bonding reactions, a large amount of energy can be released, which is quite different from burning a molecule like a methane gas. When we burn methane gas, we will break down the bonding between the atoms. The carbon and hydrogen atoms will break this bonding and release some energy. But compared with the energy released within the atom, which is the nuclear bonding energy, which is much stronger. So for the same number of neutrons, including the protons and neutrons, a uranium atoms will give 9 million times energies than burning carbon. And that's why nuclear energy is so powerful. There are a number of different isotopes for uranium. For example, isotopes 233, isotope 235, or there's another nuclear metals called plutonium, which is also commonly used in some nuclear reactors. There are some isotopes which is feasible. Okay? Feasible means it can be split by neutrons. And there are some isotopes, for example, uranium-238 is fusionable. Fusionable means it can be split with difficulties, and you need high energies to split this atom. And among different isotopes, uranium-235 is more likely to be split by some low energy neutrons. And in other words, it's easier for us to trigger the nuclear reactions for uranium-235, and therefore we pick this nuclear fuel for most of the commercial reactors. In the nuclear fission process, a neutron will hit on the uranium-235 atoms, and it becomes 236 because another neutron is added to this atom. But this is not stable, and this uranium-236 will split into two parts. And during this process, 2 neutrons will be released. Let's see the following animations to see how it happens in the reactor.
When the neutron hit on the uranium-235, the uranium nucleus will split into two smaller atoms, together with two neutrons, and the chain reactions will continue to hit on another two uranium-235 and generate four neutrons.
So these two neutrons will hit on two more uranium-235 and trigger another series of nuclear reactions. And then 2 times 2 is 4 neutrons will be produced and then trigger 4 more uranium and then create 8 neutrons and so on. So the number of nuclear reactions will be exponentially increased, and therefore the energies released will be quite huge. And this is a chain reactions. Once we trigger the first reactions, then the remaining reactions will be enormous. So if we put enough uranium fuel in a reactor, which is higher than what we call a critical mass, then the number of reactions here can trigger a continuous chain reactions, and the reactor can provide steady energy output. So commercial reactors contains about 3 to 5% of uranium-235, and also the remaining fuels will be uranium-238. In the nuclear fusion reactions, two hydrogen atoms will fuse together. But these two hydrogen atoms has a little bit different. One is a proton plus a neutron, and other is a proton plus 2 neutrons. So the atomic mass is a little bit different. One is 2, another is 3. When they merge together, it becomes a neutron plus another atom with 2 protons and 2 neutrons here. And this is what we call helium. So these reactions show us that when two hydrogen atoms, one is called deuterium with a proton and neutron, and other is called the tritium with a protons plus 2 neutrons, merge together after the nuclear fusion reactions, the two hydrogen merge and form a helium. During this process, a neutron will also be produced as well as energy. So this diagram shows the energy level of the binding energies per neutrons. So the x-axis is the atomic mass. So for nuclear fissions, so we're talking about uranium-235, where the atomic mass is large. So when a large atomic mass is split into the smaller one, so energy will be released. While in energy fusions, when a small atomic mass atoms like hydrogens is fused together, become a heavier atoms like helium, then energy will also be released. Okay, so let's do some calculations. How much energy will be released by a nuclear fissions? Now in uranium-235 will then be split into 2 smaller atoms, and these small atoms add together in uranium-235. After the nuclear fissions, it will split into 2 smaller atoms, and the total mass before and after these reactions will drop a little bit. Before that, the mass is 236. U is a unit of a proton, and then after that it's only 235.8. Okay? U is a unit of the mass of a proton. So altogether, the total mass dropped by 0.213, okay, in the unit of a proton. So if you can recall what you have learned in chemistry, so the total number of atoms in a mole is given by a molar. Okay. So this diagram shows the energy level of the binding energies per neutrons. So the x-axis is the atomic mass. So for nuclear fissions, So we're talking about uranium-235, where the atomic mass is large. So when a large atomic mass is split into the smaller one, so energy will be released. While in energy fusions, when a small atomic mass atoms like hydrogens is fused together become a heavier atoms like helium, then energy will also be released. Okay, so let's do some calculations. How much energy will be released by a nuclear fission? In uranium-235, after the nuclear fissions, it will split into two smaller atoms, and the total mass before and after these reactions will drop a little bit. Before that, the mass is 236. U is a unit of a proton, and then after that it's only 235.8. Okay? U is a unit of the mass of a proton. So altogether, the total mass dropped by 0.213, okay, in the unit of a proton. So if you can recall your knowledge in chemistry, the mass of one neutron is 1.661 multiplied by 10 to the power negative 27, which means 0.0000027 altogether, and then 1661. Okay, very small. The weight is so small, but if you multiply this by the drop in mass, which is 0.213, the drop in mass is about 3.5 multiplied by 10 to the power negative 26. Okay, very small. Even though we multiply by mc squared, c squared is quite huge, in the order of 10 to the power 16. But altogether, when you multiply them together, the energy released by one single nuclear fission reactions is only 3.18 multiplied by 10 to the power negative 11. Okay, again, very small. 0.00000 after 11 0, 3.18. Okay, but how about the number of reactions in a kilogram of uranium? Okay, so let's again recall your knowledge in chemistry. 1 mole is equals to 6 multiplied by 10 to the power 23, which means 6,000,000 altogether 23 0. Okay, so in terms of billion and billion and billion. So this number is huge. For just 1 gram, 1 single gram of uranium, we are talking about this number. Okay, and divided by the molar mass, they are all together 2.5 multiplied by 10 to the power 21 number of uranium atoms. So if all these atoms contribute to these nuclear fission reactions, we are talking about multiplying them together. Although each nuclear fission reactions provide a small amount of energy, 10 to the power negative 11, but because there are many uranium atoms in 1 gram of uranium, so the total energy is talking about 81.1 gigajoule, okay, which is quite huge. So if you compare 1 gram of fuel, let's say you go to the gas stations to fill up your car with gasolines, just 1 gram, the energy release is very minimal, because the energy output from a chemical reactions, you burn gasoline and break down the covalent bond between the molecules, is very different from you destroy a mass, a matter, and convert into energy, which is given by E equal to mc squared. So m is 1 gram and c is equal to 3 multiplied by 10 to the power 8 squared, means to the power 16. Okay, so you can compare the differences, and that's why nuclear energy is much more powerful. In the next video, we will talk about the operations of a nuclear reactor. See you.